So our next talk is by Gopi Srineni. Gopi, are you online?
Yes, I am. Can you hear me?
Okay. Sure, sure. Yes, Gopi. Yes. Hi, Gopi. So our next talk is by Gopi Srineni from Axiado, USA. So there were some questions already about security. So it's good that we have this talk on security immediately after the question. So I didn't post those questions because I knew this talk was coming next. So I'll give a brief intro to Gopi. Gopi Srineni is a Silicon Valley veteran with over 25 years of experience in the semiconductor, software, and systems industries. He was a senior executive at companies like Qualcomm, Marvell Semiconductor. He has demonstrated exceptional skill at building highly efficient, cost-effective organizations and bringing industry-changing technologies to the market. To name a few, highly popular Wi-Fi mesh networks, mobile hotspots, and network-attached storages. So Gopi is going to talk on cybersecurity product. So Gopi, I invite you to start your talk.
Thank you. Can you allow me to share the screen? It doesn't allow me to do.
It's not allowing you to do?
Oh, now I got it. Okay.
Yeah, just try. Yeah. Okay. Yes, we can see it, Gopi. Yeah.
Okay. Can you guys see my screen?
Yes, Gopi. Yes.
Let me see where you are. I gotta find it. Multiple screens.
Your screen is visible, Gopi, and you are visible.
Okay, good. Okay. Okay, sorry. Okay, I am going to talk about today's, I'm a company, sorry. Okay, now. Thank you for the intro, and just a little bit on the intro, the background also. So I am the CEO of a company called Axiado Corporation. We do a AI-driven security process, co-processors, hardware-based, it's a silicon solution. And I'll talk in a little bit how that makes change, and we do at edge and also on the cloud, both sides. And I've done multiple startups so far, and recently joined this company 9 months ago. And just before that, as introduction came out to be, I was one of the guys who created actually the Wi-Fi mesh. So if you're using the mesh Wi-Fi, if it doesn't work, you can blame me. And same way, the pocket router, so-called MiFi router, and that was one of my brainchilds at Marvell. And even before that is something called NAS, network attached storage. If you use a mobile attached storage, and that's also invention of mine. Here, the company, just background, we're around 55 to 60 people today, and we're a startup company. We're going after around $18 billion business. The problem statement is cybersecurity is not tamper-proof, and that trust is not there. So I'm going to talk about that in a bit. Before going into the size, why we are paying attention, why the AI is worth to do it an edge, and then security, need to use this AI, not at the completely cloud after the fact. And I'll talk about some of the DoD attacks happened recently also, how we could have, our technology, similar to our technology, could have been stopped this one. So before going some stats in here, and completely data breaches are out of control, and some stats in here saying there's around $6 trillion of loss per year, what's measured to this date, without including the DoD stuff. It's around close to 5.4 trillion already, and in 2021 they expect it to be around 6 trillion. And total worldwide cyber spending is around 124 billion, and that's 2019 stats. And you can see the a lot more stats in here, the national security spending itself, and Fortune 500 companies spending, etc. Just to paying attention, next stat is almost every 40 seconds there's an attack, and 4,000 ransoms a day, ransomware attacks a day reported. There's a lot more than these numbers because a lot of people don't report because they feel shy, and defamation of the company name and all that. They just pay the guys and stuff like that. On the bubbles, if you see this map, until 2017, these bubbles are smaller in size. The size of the bubble represents the size of the data loss in here. But 2017 onwards, the bubble size is bigger. The reason that's bigger is because now the data center is becoming as a service. So we're all hosting, and whether it's an Amazon, whether it's a Google or wherever, Microsoft or Azure, etc. If somebody breached into those, the data loss is bigger. That's where those bubbles are bigger. I am showing some vulnerabilities reported in the market for last maybe 10 to 12 weeks in here, 3 months attacks in here. Most of the things that I'm paying attention to, the most of the boot and boot side of it and hardware vulnerabilities in here. And anything of these, if I share this one to you guys or search these links, you should be able to get a lot more data on the internet itself. You can read through. Unfortunately, these are all serious attacks, including the last one, that so-called SolarWinds or DoD or FireEye attack, and I'll talk in a bit how that has been attacked too also. And similar to that, there's something called side channel attacks, and I'll talk about that too in a bit. Side channel attacks are something people can be on the platform, any platform, whether it is your phone or your laptop or even data center or 5G base station or network appliance. It doesn't matter. They should be able to play with your signal strength, whether it could be power supply or whether it could be clock or whether it could be anything on that. Just change those modifications in a simple attacks, and especially in automobile would be a bigger tool also, able to take care and take over your complete system. I think Flavio or somebody talked about IoT and autonomous cars, and it's this side channel attacks are highly important, and those, especially Tesla has been attacked 3 times already. All it needs is a simple approach to it, and then change whatever the trigger event. It could be just breaking it, it's an accelerating it, or do whatever it is, tamper that autonomous thing, and will be able to be serious consequences on that. So one of the examples is that side channel attack, and I wanted to give you guys something is a voltage glitch itself, and maybe a little bit too technical on the picture in here. What I'm trying to tell you is all we need to know in a simple way. This is all Google searchable for you guys, and this is nothing I'm sharing to. I'm not teaching anybody to. I don't want to get in trouble teaching anybody to do the bad things. But if you look at these pictures, if my cursor you can see, there is a boot ROM execution at the time. These are obviously oscilloscope pictures, and you can see the execution in here, boot ROM in here, and boot ROM in here. At that time, all you need to know after the turn on, and at particular that time when the boot ROM is being loaded, when it is doing a loaded, and after the load, you're going to go check for your hardware root of trust and a hash algorithm to see this is your identity, it is, and all that. You don't need to do anything. All that attacks we just talked about is attacking through that, coming back and breaching into and able to steal your keys and stuff. In this simplest attacks in here, you just need to glitch the voltage at that time, voltage or current, and I'm giving you one example of voltage. So all you need to find out when that is. If you get the glitch on that time of the voltage, and all the algorithm for everything is deployed so far today, it will give you that you passed that whatever the test is supposed to be. That hash is already checked, and you get the yes signal. What that means is now the system is authenticated without a real key. Somebody should be able to come up, and once you authenticated, whether it's a firmware, whether it's a malware or something authenticated, you got the control of the system, and you should take over the flash, and you will be able to take over the system by simple increasing the voltage. And good and bad about this is, and if you go to an ATM, you type in punch in the numbers or whatever the passcode, 4-digit number. And if you try 4 times, your password is, that's not, you try too many times, it locks the system. Same thing with online password, you try to do it. Unfortunately, in here, there is no lockout system. So how do we get the 1.8 milliseconds exactly? He can try 100 times, 1,000 times, 1,000,000 times. Unfortunately, no system stops it. So that means anybody should be able to get this one once you know what to do this. And once you got it, and afterwards, it's pretty vulnerable. So these are serious attacks, and some of these are used in the DoD attack also in a simple way to come into the systems. Any questions? I'm sure a lot of questions on these guys, and when the presentation is finished, I'll answer those. And I'll take in a small explanation about what is this DoD attacks exactly happened. Okay, what they did is blend in, and they come up like, and you basically normal people come in and they learn the host names and then IP addresses of where the data is, there at this point it's a FireEye. So make it legit type, and they inserted this FireEye open source compilers and also distributed compilers. their stuff is inserted a while ago, not today. So it make it as legit that the guys are actually downloaded. Unfortunately, we all have a system to upload. When there's an open source piece you're taking from a cloud where there's something comes up, you continuously update that. So they make it legit look like. And they inserted this Trojan, backdoor Trojan in here, where it continues changing the DLL files and something program called Orion. So this, if you guys read through this or not, but there's something called Orion, which is a defense tool system, which is U.S. government and pretty much most of the people use in the U.S. And that tools is been hacked. How did they hack them? I'm trying to explain in here. So once the DLL files has been changed, and once you got into that rumor, that gives you remote access to these FireEye systems. FireEye guy companies reported 2 months ago saying that we feel like somebody came in and it must be government and nobody bothered. No, I think maybe US government was busy with elections and all the stuff and they didn't bother. They thought it was a government thing, but unfortunately it was not. And then they're able to sniff down. So there's a timer for this, how long it will be able to do. And you wait until that compilation when this happens. So they kind of learn everything inside out and sit down dormant for a couple of weeks and learn exactly the profiles when you get to executables. And that's what the hiding in a common site where I talk about, and then come back and attack exactly. It's like, if you guys watched any of these action movies, there's a light goes on a jail or any protection environment, and the light goes around circle 360, and you're only acting when the light is not out. So when the focus light comes on you, you hide and come back and do it, exactly what they were doing. And mask the malware inside the systems itself. Normally, we all check on the malwares on a regular DDR type of things, but what they were doing is on chip in memory, they were masking there. Unfortunately, there is no checks in today, and that's also a piece of the puzzle on that. Again, there's something called Cobalt Strike and tear it up in the use. Not going into much more details on that. We should have been able to stop all this, our technology. I'll talk in a bit. Our technology is in a coprocessor sitting on every platform, whether it's an end or cloud, and has a network, neural network engine or a CNN engine we call. That's able to, it's called Secure AI, brand name is, able to detect all this anomaly, what's happening. We get to learn, able to do that on the system. That's what the edge AI comes up. Okay. All these guys use a simple concept. Any software, whether you use a Zscaler, Zero Trust, or anything, what Flavio talked about, industrial IoT said, and everybody trusts something called hardware root of trust. And what is a hardware root of trust is a unique ID for each platform. Unfortunately, that is being broken in the different ways I just told you. How you bypass that, once you bypass and come back and do it, normally what happens is this is what holding the keys, and that keys are exposed. Unfortunately, every platform is open. And people do it based on a hardware secure processing unit, and then something called software enclaves or secure enclaves worked on that. All these are being vulnerable at this point based what is in the market. So today, everybody of these solutions uses something called hardware root of trust. That's what I just talked about. Hardware root of trust is only trustworthy. Doesn't matter how great of a key or unique ID you have it. Once you transfer that root of trust handling to a software, and that software can be completely broken now. Once it's broken, it becomes a rat race of who is outlawing and others and able to outsmarting and others to be able to access it. That's what the problem is today. It doesn't matter you have a unique ID, but that unique ID has been already gone. So what we do with our technology, there are 3 types of technology in ours, and without too much revealing to you guys our proprietary information here, we are replacing something in the market, something called Secure Vault. Secure Boot has been used in the market. We're replacing that with a Secure Vault. Vault by itself is a name that it's a storage, and we will not be able to show any keys to the software. Remember the statement I made? Your hardware root of trust is only trustworthy as long as the chain of trust is not handed over to software. So what does that mean is, wherever the keys you have it in a secure boot, you're able to transfer that to DDR, and then the software started seeing it. Once he sees it, he can copy that. So malware can be sitting and doing that. Here, what we change is we never share our keys, our platform keys to anybody. It's completely protected in our keys. And we only take what authentication you need to match it, or CRC, a hash algorithm to come to us. And then we authenticate and give it a yes or no. That's all it is. So that way we never expose. And also none of the outside world knows that we existed on the platform. They're all attacking the main processor, but we're only on the outside separately saying that, like that's why we call it a watchguard processor. So all biometrics, whether it's a password, whether it's a fingerprints or your facing, eyeball thing, everything is stored inside of this with encryption keys and special encryption. And then we also able to do a complete server management or device management or user management in a hardware rather than a software in here. The second technology is Secure AI. This is an AI engine inside, which was it's approximately around 5 teraops of functionality in here. What we do is multiple applications in here. Number one, and once we are in the system, once you boot is, all integrity check happened, boot came up. Once the thing is on, then we will become in a monitoring thing. We start learning every interface of the hardware, what you have in here, whether it's a USB, I2S, Ethernet, doesn't matter what it is. And we are able to learn and build the self-learning profiles on that. You don't need to push any rules engine. We'll learn. There's no training needed. We'll get to learn it each, whether it's simple USB itself, what type of content is coming, what type of time of the day you're coming in, and what kind of functions you're doing it, and then go to the next level, even user level. Whether it's Tom came in and Abhay came in, or whether Gopi came in, what he was doing normally versus today, what he's doing differently. So any anomaly will go a double authentication detection and all that. So we're doing that on the platform. Normally what happens is that's all done in the cloud, and after the fact you find, but we're able to detect right there what's happening. So if you go to industrial IoT, somebody trying to plug in a USB stick in there and then trying to install some malware, we'll be able to detect right away that USB was dormant before suddenly it's doing something else. We're able to stop. Then I talked about the DoD things. Inside the memory itself also, they were saying something else on chip memory rather than on a DDR. That's also we're able to monitor and say, hey, there's something else is being stored in here, which is unlike of what it was before. So we're able to flag those things too also. So we'll be able to running a complete TE, that's called trusted execution environment, inside of this AI engine, and then you can change this anomaly detection completely on board and perfectly use. And use case for one of those is also, we're working on two sides. One is in a security processor, co-processor for the data centers and other applications, and the other one is for industrial IoT edge processing. So we're working with a company who will be building a single board computer right behind your hospital bed, where all probes are connected to the patient. When you connect it to everything, today, all monitoring is happening on the software at a nurse station, versus we're able to predict and able to detect everything at the patient level itself, and then able to make whatever the corrective action there itself by saving the precious time in there. And the third one is a zero attack path. The technology is Zap, Zap in the bugs, that's our brand name. It's a full stack solution for us. We are a mini-me on the board. That mini-me system has to be completely tamper-proof. We provide everything. And bottom line in this functionality wise, going back to the previous slide, on the board today, there is something, a boot chip separately, and there is an administration chip separately, and the monitoring chip separately, and then you have software called Eclipsium type of software. These are secure enclaves. We're able to replace all that into one comprehensive solution. That would be our solution, and we do have a customer traction, and every server networks is actually working with us right now, and every base station guy is looking to work with us. So we will be able to deploy this technology in 2022 platforms to the market. In product-wise, it will go to approximately pretty much every product family in the world. I'll stop there and ask for questions. I think I got 9 minutes more.
Thank you, Gopi. I think we have time for questions. I'll just so.
Do I get to read the question, or are you going to read for me?
Well, I am going to post it to you. It'll be like you'll have. Okay, so Gopi, you had a certain slide 10. So the question is, can you elaborate on the increase in power consumption after an attack?
Like, okay, that's a side channel attack, I guess. That's what he's talking about.
Yes.
Yeah. So By the way, those attacks are simple. You're able to, once you're able to get the control of the system, and which is called control and management side, whether it's a BMC or, if you understand what the BMC is, baseboard management controller, and where platform control is managed. So you're able to go and poke the PMIC in a power management chip IC, and you can increase the voltage itself. When you increase, obviously power goes up. One is obviously thermally, not capable, but increasing itself. I showed an example of how you take over how you bypass the algorithm where you're doing the hash check itself. But you can actually cause the thermal issues itself, and whole clocking is completely goes away. Data is garbled up because you're shifting the clock and everything too also. Okay.
Okay, Gopi, the next question is, how much voltage surge is allowed? Too much can damage the system itself. Is there any effect of frequency?
Yes, I think I was saying the same thing. One is the voltage is allowed is only 10% plus or minus every time, whatever the range. If it's 1.1 volts or 2.2 volts, DC I'm talking about. So once it comes in there, that's what the range normally, any circuit design, any chip design happen to be that percentage of 10 or 15% can margin, it can take it. These surges are, it's enough that surge. Within the surge, so it cannot detect, even the 10% surge in itself is delta change, will be able to bypass what I'm talking about algorithm. But if it goes further, yeah, you'll damage, you burn the chip. If you go higher, you burn the chip, or you go the clock completely up and down, you will garble the whole data, and everything goes back again with a complete status of wrong status of the chip.
Okay, Gopi, the next question is, how is AI-based security different from trust zone from ARM and Intel processors?
That's the good question. Okay.
Yeah,
yeah. So if you remember that there's a circle I showed in a hardware root of trust. So secure zone, a trust zone, what has been ARM cells, they use a small logic in that to create that logic as to where the keys and hash algorithms are done. Along with a trust zone, they use a small M3 controller for ARM, which is a simple microcontroller, to process that. When you do the small microcontroller, there's a limited functionality you can do, and you're not running an antivirus type of thing while you're actually doing the hash checks and stuff. So that's called a bare metal state. So when a chip is in a bare metal state or a system is in a bare metal state, you don't have any checkings around it. Whereas on our AI engine, what we do is while you're doing that function, I'm also checking around. Think like you have a guard in front of the house. Is not a one guard, there are two people. One is doing the functioning, opening your lock and door, and then one is watching out for you. So that's the changes in AI. We are the watch guard around you, continuously watching. While you're opening, you don't want somebody to see it. So that's exactly the difference between what Trust Zone ARM can do it and what it can do. Yeah, Trust Zone gives you a lot more keys and secure and all that, but openly you're typing something, and that's exactly somebody can be stealing what's happening. And then we do that, not allowing that to happen.
Gopi, the next question is, what are the vulnerable areas of cloud computing which are prone to cyber security attacks?
Number one big problem going to be in the world is a false data training. Everybody now running around AI, I'm sure in this conference also, we all been talking about completely the AI and machine learning and everything. Unfortunately, those machines can only learn what is being fed to them. There will be a lot more attacks. This is the biggest attacks going to come. Mark my words. It's not there yet, but it will be training the data to be wrong data. So as long as you train the wrong data, and decisions will be done wrong. And once it is done that wrong, and you cannot control because that's what is being trained. That's the biggest thing. And how do you get that? That's why we are addressing the problem. How do you get that access to give it bad training, bad data? You have to have a trust agent, right? So that trust is the one which we're trying to address. If you don't, based on today, unfortunately, people can get in different ways to train it bad way.
Okay, I think we are done with most questions. Yeah, there is this question. I don't know if you can answer this, but we'll get an answer. Is there a specific IEEE group which talks about issues in authentication, authorization, and encryption key exchange related to cloud federation?
I don't know about the Cloud Federation side, but OCP group, Open Computing Platform group, does this keys and all that authentication is being done. Maybe somebody else can answer the IEEE side. I don't know what that. I'm sure they should be. They are same common technology guys.
Sure, Gopi. I think we are kind of done with the questions on your talk.
Okay, thank you.
Now, Gopi, there's one more question. We have a couple of minutes, so I thought I'll just pose this to you. How are Ryzen processors advanced as compared to Intel, and are they less prone to cyber attacks?
No, both are the same concept. In our view, our glass of view, where we're looking at it, whether it's an x86 or ARM or even x86 from Intel, x86 from AMD, it doesn't matter. Everybody uses something called secure processing unit and a trust zone combinations inside of their host processor. Unfortunately, that is what we're claiming to be vulnerable. So not one better than the other. It's all more of how much computing powers are used. AMD uses a little bit of outside with RISC side combination. So they can claim they're a little better advanced, but there's not much. We say it's simple. If the fire station is on a fire, there's nothing, it doesn't matter how much of tools are inside, you're already on a fire. So if the processor has been attacked already, there's nothing tools you have, it is anything to do better. So you had to be outside to solve. That's our pitch to be telling. Just like an all AI offload you're giving to outside to do functionality, this is also security offload. So in our view, there's no difference in it.
Okay, Gopi, thanks a lot. So for your excellent talk and all the questions that you took. So thank you for coming and sparing your time to give a talk.